Why didn't you tell me earlier? Half an hour gone. Anyway,
So I also
thank
just
you.
realized.
Okay, thank you. Yes, so others are, Brian, do you want to chip in? Yes, because Lynn and Vanessa, they got it right. It is because these UV visible spectroscopy, it cannot detect the color, the concentration if there is no color. If it is a watercolor or colorless, then it does not get anything from here, right? You don't get anything from here. Only if it is colored. But for AAS, it does not depend on color. As long as there is a metal inside AAS, you will get something from the AAS. And yeah, thank you very much. Copper sulfate, it is actually color, greenish color, so that you will get something, some color absorbance by UV visible. Now the question is saying which of the following steps in the analytical procedure is associated with one of these techniques but not the others. Since this copper sulfate can be analyzed by both ways, but which of the procedure is we are using for one of them, one of the technique, but not we are not using the same technique, same procedure for other technique. Option A says that determine the wavelength which is strongly absorbed by copper ions but not absorbed by any of the other substance in the solution. Yes, because when we do the AAS, right? When we when we do the UV, we carefully check or we carefully take the wavelength of light that the sample will absorb the maximum. That one we check, carefully decide when we use the UVVs. But for AAS, we do not care. As long as it is that range of light, so for the sodium light or copper light, we just take that one. All right? So this is the correct answer. Question number 9, it says that which of the following chemical solution can be quantitatively analyzed by a colorimeter? Quantitatively. What do we understand by quantitative? What do we understand by quantitative? Anyone? Eric?
Like any amount?
Yeah. So there are two terms, right? Qualitative and quantitative. Qualitative means like what you cannot quantify or you did not quantify. Quantify means you did not put any unit. For example, the food is very nice. The food is very tasty. Or the sky is very, no, it can be quantified as well. The weather is very pleasant, right? So these things that we cannot quantify or we do not put, like we do not put in a unit that the weather is 5 degrees or 5 ringgit beautiful, right? We don't do that. We cannot do that. That's why it is the qualitative. But quantitative means this pen is 5 ringgit price. That pen is 7 ringgit price. So we quantify the price. So this is quantitative. Or this is 5 ringgit. So this is better than 3 ringgit or something like that. So quantitatively analyze by colorimeter, and then by colorimeter we do not only see the color. Since it is quantitative, it means that we do not only decide which one is what color, which one is green, which one is blue, which one is red. We do not only find that one. Colorimeter can find that one, right? That this is green range, this is yellow range or whatever. But also, this question is saying that it not only that we find what color, but also we find which one is more green, which one is much more yellowish, right? Or 10 unit of yellow more than that one. Using which one? Both A and B, I mean 1 and 2 should be the two things. The potassium permanganate, it is deep purple color. Yesterday we saw it, something like that. It is purple color. And copper sulfate that we have already seen that it is green color. But sodium chloride, it does not have any color. It's just the table salt, right? If you add table salt in water, it does not change any color. Unless there is some pigments, you put some color only. Then otherwise, if you just put some sodium chloride, that is our table salt, in water, it does not show any color. So only 1 and 2, these two can be used quantitatively. Question number 10 says the graph shows the absorption spectra of 3 pigments in leaves: chlorophyll A, chlorophyll B, and carotenoid. Which of the following is the best wavelength to determine the concentration of chlorophyll B? Only chlorophyll B I want to determine in a solution containing a mixture of all 3. So here, actually this photo, or what you are looking on the screen now, right now, you are looking at some figure, right? Wavelength, nanometer, absorbance. This figure has been constructed after we have taken the absorbance of all these 3 different chemical, or you can say component, individually, right? I have taken a graph paper. I put in y-axis absorbance, in x-axis wavelength, and then I have put the chlorophyll B. First, I took the chlorophyll B and then I saw the absorbance, and then I draw it according to the machine that give me the absorbance. And on the same paper, I put the value of carotenoid and chlorophyll A all together, one after another one, and then I just showed it by the dotted line or a dash line or a solid line. That's it. I have drawn it 3 at one time. But if I put all 3 of them in the machine, in the UVV's machine, all 3 in the cuvette, right? I put the mixture in the UV, in the cuvette and put it in the machine. What I will get is just this. According to my red drawing line, I will get this type of curve. Not here it will not come out, here it will not come out. This is what I draw one after another one. But all 3 when I put there, I will get only one solid line like this. And this solid line means all 3 together. Right? All 3 together. So when there is a mixture and I want to find out which one is the, for chlorophyll B, is it? Chlorophyll B. I want to find out only chlorophyll B when there is 3 of them together in the mixture. Which of the wavelength should I set in the machine? Should I set 500? If I set 500, at this wavelength, this chlorophyll B is chlorophyll B is here, right? At 500, chlorophyll B, it shows that it absorbs quite much, but this same wavelength is also taken by carotenoid. This dotted dash line is by carotenoid. So same wavelength carotenoid also takes up. So if I, even though chlorophyll B is absorbing this 500, I set 500, what will happen is maybe these the machine will be confused with this same absorbance, and then it will give me some, probably something like a bit bigger line, because it will, the machine does not know what is chlorophyll or what is carotenoid. It just read the absorbance. So probably it will be confused and give or our curve will be impacted by other thing. So it is not alone. I mean, it is not the perfect one. But if I take this 600 and around 30, 40, something like that, here I see there is none other, the chlorophyll A or carotenoid, none of them are absorbed at this light. Only chlorophyll B is being absorbed, or chlorophyll B is absorbing this wavelength of light, that is 630. None other is absorbing. So this nanometer of light I can use to analyze the chlorophyll B sample. Okay, so 630 is the correct answer. And same thing goes for red number 2. So if, even though the red number 2 maximum absorption is happening here, right? It is happening here around 540. But if I take 540 nanometer, if I set 540 nanometer in the instrument or in the machine UVBs, so what will happen is this machine will be confused with blue number 1 concentration as well. So this machine will read blue number 1 and then red number 1, 2, and then it will give based on the both of their absorbance. It will absorb both, and then this curve will come out based on the both absorption. But if I take around 500 like here, or let's say that 505, it is here, there is nothing else. No, none other are being absorbed at this light. So it's only red number 2. So 500 or 504, 505 can be used as well. I mean, should be used to detect this. Question number 12. In preparation of a series of standards for calibration of colorimeter, a stock solution of 0.1 molars nickel sulfate, nickel 2 sulfate, right? Okay. Nickel sulfate solution was required. To prepare this stock solution, 15.5 gram of nickel sulfate solution be added. To prepare this stock solution, how many gram of nickel sulfate should we be taking? Again, N equals C into V. And then the concentration is already given, that is 0.1 molar, and volume is 500 milliliter. 500 milliliter. So it's 0.5 liter and 0.01 mole. 0.1 molar, a mole per liter. From there we find the number of moles of nickel sulfate, and then to find the mass we just multiply by molecular weight so that we find the mass of it. Question 13 and 14 are related to the forming question. Okay, chemists suspected that an impure copper lump contained a significant amount of cobalt. Cobalt would be oxidized to cobalt 2 ion that would remain in the electrolyte solution and can be analyzed by UV visible spectrophotometer. The following absorption spectrum gives the result of the analysis of the solution. Cobalt 2 and copper 2. Hold on, yeah. Okay, the question is saying the cobalt and copper 2 ions absorb distinctively in different wavelengths. Which of the, of course, that is cobalt is 500 something, 502, 500, 500 something, and copper, both can be used for copper is either 980 or 840 something can be used for copper. But yeah. A calibration curve was constructed using a series of cobalt using the concentration, and then the same question, same thing. It was 0.350. So it was 0.350, and then we drop down. So it is 0.06 molar concentration, right? We find it. Same thing. I'm not going to discuss. Only it is 54. So whatever we get, let me just go through quickly. Using the standard protein solution, the calibration curve shown below are obtained. A sample protein was 54 diluted and the absorbance was 0.3. So absorbance is 0.3. That means here, and it is 130, probably 130. And if this type of question in the exam or test, so what will happen is you have some range, like for this type 130, 140 is allowed, but if anybody say 110, that is of course wrong, right? Even if using our bare eyes, we can see that it is 100, not 10, not even 120. Maybe 130 on 25, 30, 35 should be. Within this range, it is acceptable. But if anyone say 140, that would be wrong. 110, that would be wrong as well. So it is 130 to 135, and it was 54 diluted. So we have to multiply with this 50, and then we get the correct answer. Okay. So now, any questions so far? Anybody has any questions so far? No question. Past examination questions. It was the descriptive question, and we know that lead, why AAS is suitable to be analyzed in the leads. Ions in water. It is already given, but I want to know how many of you have checked. Erlin, what is, why AAS is suitable, not the UV? Erlin, Munib. Hello, Munib. Why AAS is suitable? Chamad, your network okay, or your microphone okay now? Vanessa, no one is replying. I have to rely on you then. Vanessa.
Yeah.
Yeah, so what is your answer? Why is it so? Why AAS is suitable method to be analyzed? Concentration of lead ion in water. First of all, lead is a metal, right? Lead is a metal. Lead, sometimes it gives a distinctive color, depends on what type of salt it is. But the problem is here in the water, you just need to mention that because lead is metal and it is suitable to be atomized or vaporized, right? It can be vaporized or atomized in the AAS machine when we inject it in the high heat and the flame. So it can be atomized and then it can absorb. But the behind this, the answer is, although lead sometimes it will depends on what type of salt, it will give you color. But the thing is, in the water, the lead, the mercury, arsenic, what else? Iron, then all other metal, carcinogenic metals in the iron, in the water are very small, a very small amount, trace amount there are. 5 ppm, 0.1 ppm, something like that. And in that concentration, it does not give you any color. So it will be not suitable to be used by UV visible or colorimetry method only by AAS, because AAS is very sophisticated. It can find the concentration of 0.01 ppm, right? It is so sophisticated, and that is why it vaporized here. All right, so this is the same thing. Calibration curve was plotted against the standard solution with known concentration of lead iron, and then you know what to do. 100 decimeter cube is 1 liter, yeah? So after you find the absorbance at 0.55, and this 100 decimeter cube, now every time we have seen that it is diluted, right? It was diluted, but this time it has been boiled down to 7.5. That means, what have we done here? Can anybody tell me what have we done here? What happens here actually? From 100 liter or decimeter cube to 7.5 decimeter cube. What actually happened? Upathi?
So I believe it's boiled, so it disappeared, I guess so. Not so sure.
Yeah, it's boiled, of course. What happened actually? The concentration? Noor, you want to say something, yeah?
Increase in concentration.
Yes, the concentration has been increased. Every time we decrease the concentration by diluting, but this time we have increased the concentration. But now, Noor, why do we have to increase the concentration?
Is the absorbance too small?
Yeah, exactly. It is too diluted that the machine cannot pick up. But we know that there is something here. So what we'll do is we increase the concentration, and then we find out what is the amount, or what is the concentration of the solid, the lead or whatever in there, or the water, right? All right, so how many times have we increased the concentration? 100 over 7.5. So it is 13.33 times the concentration was increased. The absorbance of this concentration for after it has been increased to 13.33 times, it was found that it is 0.55. 0.55 in the we have to find out the concentration in original contaminated drinking water. So 0.55 means it is 5 here and then 5, 1, 5, 1, 5, 2, 5, 5. So around here actually. So my God, it is a bit tough for me to draw. Okay, so it is not exactly there, but something somewhere near there. And this line should be between two lines. Okay, good. So now it is here. So it is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 7, 1.75. No, sorry, 1.075. 1.075, right? So this is what I'm doing. Yeah, this is 1, so this is 1.1, and then each, the segment is 0.02. So 1.1, 1.1, and then 0.2, 0.4, 1.15. Yes, so it is 1.15. The concentration is 1.15 in the concentrated solution, right? In the concentrated solution, this is 1.15 or 1 something around that. Not 1.2 or 1.18, but 1.4 to 1.5, 1. Let's say 1.16, around that should be okay. Okay, so in that case, what we have done, it is 13.33 times increased. So we have to divide by 13.33 times so that we will find the concentration in original solution. So 1.15 over 13.33. So it is 0.086, right? 0.086. Yeah, about in that case 0.086 it should be. Okay. Is it permissible if the permissible concentration of lead ions in the water is 0.05 milligram per decimeter cube, milligram per liter, that means ppm, 0.05 ppm. So is it safe to drink the water? No, it is more than 0.08, right? We get 0.086, something like that. So no, it is not safe. It is much more than 0.05. So it will not be safe to drink that water. Question number 2 says, what is the function of a monochromator? Right? So what is the function of a monochromator? It is, this is the monochromator. This is a prism. This is a prism. Have you seen a prism? Anyone?
Yes. Very colorful.
No, prism is colorful. Upati?
So I think I'm mistaken for something else.
No. You have not mistaken. Actually, you have described it in mistaken way, but you are correct. I understand what you mean, but I want you to describe it or try to describe it correctly. By the time you do it, I go and bring my tea. Yeah?
Ah, yes, bro. It is. Looks like a pyramid.
Found it?
Yes.
Yeah. What is that?
It is a pyramid which has monochromatic light colors.
No, I mean, you're describing a prism, isn't it?
Yes.
Okay. It's a pyramid of.
Consists of 7 colors.
Mhm.
Because
Okay.
that's what monochromatic means, right?
Yeah, not quite, not quite. So let's see others if anybody has any other way to describe it. Eric, haven't heard from you the whole day.
Yes. What is a
Yeah,
prism?
yeah. What is a prism?
Just anything like it's like a shape with like top and bottom they have the same shape as long as it has the same shape, right?
Top and bottom have the same shape.
Yeah, like a triangle at the bottom and a triangle at the top.
Okay. Triangle is triangle.
Yeah.
The top is always sharp, pointed.
Not sure. Am I talking about the same prism that I know?
Okay. Chamod, your microphone okay now? Munib, anybody? Anybody? Yeah, good, 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 Brian. A prism, actually, it is the answer is mixture of all of your answers. Yeah, it is made up crystal. It should be made of crystal, but with the glass you can also make. The better way is the better its transparency, the better light it will pass through. So it is a triangle which has equal side. What Eric was telling, the same top and bottom, it is equal. The sides are equal. The angles of the what do you call it? The sides, right? All the same, same side. And then one light comes in, one's beam applied, and it can disintegrate that light into seven different color. So if this light is coming from the sun or from the light is coming, it will come from one side of the prism, and then it will be separated into 7 colors. And so we see that separate color into our eyes. We can distinctly see the color. So this is if light is coming from one side, it is going separate 7 color. So if we use it in inverse way, that 7 color of the light that is coming from the sun or from the anything, then we can get it only one single nanometer or wavelength of color from it if we select it in a smart way. So that is the thing that a monochromator will do. So, and moreover, there is a slit, and the sources of the radiation will produce one single nanometer of light. All these lights are the single nanometer wavelength, single wavelength. But so this monochromator, the light is coming through a slit, a very small opening. All right, it is coming from through this. This monochromator will find out, and it will further reduces that the light is coming to one single beam. Just one single beam it will come. It will allow to come through this. So that it is going from here, one mirror is directing some color, I mean, some 50% of this light to go through this reference cell, right? And then at the same time, and the light is going and then to the detector to find out what is happening here. The reference cell here is we used some of the UV visible instrument, this reference cell used in parallel in like this, so that we keep the reference cell all the time. Yesterday we saw that we took the reference, put there first, and then throw it to make the 0, 0 or setting the 0, right? 0 absorbance. Yesterday we used it. But for some of the instrument we have seen, we have in our lab that we put the reference cell all the time and then just the sample we change. So all the time the instrument is measuring the light or measuring the detecting the light that is coming out from the sample based on the reference cell. Okay, based on the reference cell. So this is the good thing. Okay. Of course, it is 450. You can see. Okay, so yeah, I want to talk about this. Not much. A calibration curve was plotted using absorbance values of 4 standard solution of ferrous thiocyanate. And just like yesterday we have done, right? The lab report or lab data, we know the absorbance, but you have to find out the concentration by calculating the dilution factor. What we started with, it was 6.0 something times 10 negative third of this iron ferric chloride, and also the same as per the manual we have. Let's see how was it. Yeah, 6 times 10 negative third molar of ferric chloride, and we took it. And 150 milliliter, 50 ppm of sodium salicylate. 150 ppm sodium salicylate that we took yesterday, that means 150 milligram per liter sodium salicylate. So this sodium salicylate, when we use as a blank, so it should be 150 ppm, right? Let's say we are doing this for our lab. So we got an absorbance at the beginning at 0 sodium salicylate, that is 0.00, we got what? 0.00, right? We set the blank 0.00. But for solution 2, we got 0.02. 0.02, it should be here, something like that, 0.02 at. So we need to find out the concentration, how much of the sodium salicylate was in the solution. And for solution 3, we got 0.44, so it will be like here, and we have to find out what was the concentration of sodium salicylate. You need to calculate. And same goes for solution number 4, that is 3, 4, 5, 0.85, 0. Something like that, and here as well. So unknown sample that we found, if we draw it and then drop it down on the x-axis, wherever it matches, it is our unknown sample concentration. So this is one. And after you find all this data, right, the concentration and the absorbance, you can do this type of curve on Excel, Microsoft Excel. The Microsoft Excel will give you all this type of equation. From that equation as well, other than using this to draw on the paper and drop it down on the x-axis, we can find it easily from this type of regression analysis. Okay. we just put the y value. That means unknown was 0.124 or something like that, 0.15 unknown. That should be, we put in y value is the unknown one, and then we can find what is the x. X is the concentration, right? X is the concentration, y is the absorbance. Y is the absorbance. So it's concentration and absorbance we found, right? From there we can find what is the concentration of unknown. This equation actually will work theoretically beyond the limit of our known or standard solution. Like I have standard solution until 0.001, like here, right? I have until here. So if I get an unknown sample absorption point 4, I can say, okay, it will somehow match here, and then I will get the result here. But this is not true, because I did not do the standard sample beyond this point. If I had taken another standard sample, we do not know whether this line will go straight, or maybe that sample, standard sample, if I take like here, it will be here. So this line does not go through this way, rather it goes through that way, right? So probably it would not be the true. It will be, in that case, it will touch here and then it will be here, right? In that case. So that is why if this unknown is not within the range of our calibrated sample range, it is not very accurate result. Okay, so now this is the last one I'm going to do. After that is the same thing. So here it says that analyzing the manganese content of steel, because in steel we need to add manganese, chromium, vanadium, and many other things. So that is why in the iron, if you keep adding all those things, the iron becomes steel. And it becomes more steel, you know, stainless steel is very strong, very hard. It does not rust, and it lasts very long. So many things it has. But iron, on the other hand, it is not many things we can do with only iron, right? It is fragile. It breaks. It's not workable. So anyway, so manganese is one of them that we add into iron to make it steel. And we have to make sure always how much manganese we are putting. If too much manganese, then iron is not steel. It is very much fragile again. So manganese can be find out by using this titration method of periodate solution ion, or potassium periodate also can be used. And if we use that one in that reaction, the oxidation reduction reaction goes this way. So manganese is 2 positive ion, then iodide actually, which will form the iodate, that is IO3, iodine trioxide, in that way. So, and it is, if you notice, it is in the acidic, in nitric acid. So it is an acidic medium. It is happening in the acidic medium. How can I change, or how can I find out what is happening when this IO4 is changing to IO3, right? IO4 is changing to IO3. Since it is an acidic medium, what will happen is I have a lot of hydrogen, and I do not have to bother with how much hydrogen I need to add because it's an acidic medium. So hydrogen I can just add, and this excess of hydrogen, it will produce water, and one oxygen is left, oxygen atom, so it will produce 2 hydrogen. That means 2 hydrogen I have to add. 2 hydrogen will have 2 proton, and then this 2 proton I will have to add some other you know, what do you call it, electrons, because it is hydrogen I am adding. I have to add the electrons as well to balance, and from there I see that on this side this is one negative ion, this is one negative ion, but here there are 2 positive ions, so I have to add 2 electron on this side. So 2 electron and 2 positive ion, it will be crossed, only 2 negative and negative on other side, so it is balanced in this. So this equation is balanced in this way, right? What is the oxidation state of iodate ion and iodide ion? Oxidation state of iodate ion is here if we find out from the same method that we have done, that iodine, right? Let's say it's X. It should be positive X because oxygen is negative already. So negative 4 times 8, 4 times 2 is equal to negative 1. So it is positive 7. Iodate ion is positive 7. And for iodide, it is positive 5. So since from positive 7 to it reduces to positive 3, it is reducing, right? So positive 3. So it is the oxidation or reduction reaction then. It is being reduced to 5, from 7 to 5, so it is the reduction reaction. Again, the same thing, you have to find the concentration from here. Okay, so this is pretty actually the same thing that we have been doing, and curcumin powder, standard 1, standard 2, standard 3, we find out, and then from there we'll find what is the unknown milligram per liter. We have to draw it on the graph to find out the milligram per. It is already in gram per liter, so this is called milligram per gram, curcumin content, milligram per gram. So from here we will find milligram per liter. We have to convert it to milligram, gram to milligram, and then gram to gram as well. Okay, so this is it. Now, do you have any question? Anybody has any question? No, no question. Okay, so if no question, then this is it for today.